Hello everyone, and welcome to IIT Hyderabad ACM chapter's newly introduced initiative called ResearchConnect. And in this particular initiative, we are aiming to connect researchers around the world in the fields like systems, theoretical computer science, and machine learning by letting them share their work and experience. So in today's we are having our first session, and today we will be having Steffen and Evgenia, currently working as a PhD students at International Max Planck Research School of Intelligent Systems. They will be delivering a talk on making neural network robust against common corruptions. And along the same lines, they will present their works published in ECCV and Europe recently. So, just a bit about Steffen. So, like his research interests are in domain adaptation, multitask, and self-supervised learning. And previously has worked on self-supervised representation learning with Michael Ollie, Alexei Vyvsky, and Ronan Corbett at Facebook AI Research. About Evgenia. So in her PhD, she is working on different strategies to achieve robustness of neural networks against adversarial and natural distortions. And her aim is to make autonomous agents robust to bad weather conditions, which currently poses a big problem in areas like object detection and scene understanding. So taking no more time, I would request Evgenia to take from here and present the work accepted at ECCV. The work is a simple way to make neural networks robust against diverse image corruptions. Yeah, so over to you, Evgenia.
Okay, hello, I hope you can see my screen and I hope you can hear me.
Yes.
Great, okay, hello everyone. And my name is Evgenia Rusak, as you heard. And this is joint work with Lukas Schott, Roland Zimmermann, Julian Witterwolf, Oliver Brinkmann, Matthias Bethke, and Wieland Brendel. I'm happy to show you the work that we presented at the ECCV conference this year. So in our paper, we address the problem that neural networks are often very susceptible to image corruptions that have not been part of the training data. A great data set to measure robustness is ImageNet-C, which consists of 15 different corruptions organized in 4 main categories of noise, blur, weather, and digital that were applied to the validation set of ImageNet. Our first idea to increase robustness is to add Gaussian noise to clean images and train a classifier, here a ResNet 50 with augmented data. And with this simple method, we measure an increased accuracy on ImageNet-C. However, since there are several noise types in ImageNet-C, it is expected that the performance would increase if we train with Gaussian noise. So we also measure the accuracy on ImageNet-C without noises, where Gaussian noise training, interestingly, also improves accuracy. And for reference, this ResNet 50 has a performance of around 76% on clean ImageNet. Okay, so these results were obtained for sigma, the standard deviation, or Gaussian noise of 0.5. And what happens if we vary sigma? So first, let's use different colors for ImageNet and ImageNet-C without noises. And ImageNet-C without noises will be blue now. Okay, now let's mark the accuracy for clean training. Like this. Yeah, let's mark the accuracy for clean training at sigma equals 0 and the results for sigma equals 0.5. What happens if we decrease sigma from 0.5? Okay, so the accuracy goes down. And what happens if we increase sigma? Okay, so we see that we get the best results for sigma equals 0.5. Data augmentation with Gaussian noise is not new, and other works have tried using it as well, but did not see any benefits, or the effect was rather small. And here we show that sigma is an important hyperparameter, and if it is not chosen properly, then the gains in robustness are not as strong. And other works have used either too large or too small sigma values. Okay, in this slide, we will look at some methods from the literature that help increasing corruption robustness. In this results table, we'll look at the top 1, and top 5 accuracy of differently trained models on ImageNet and the corrupted ImageNet-C. For ImageNet-C, we look at full ImageNet-C and ImageNet-C without the noises. And first, I show you the baselines we compare to a vanilla trained model, a model modified to enhance shift equivariance using anti-aliasing, a model trained using Gaussian noise patches, a model trained on stylized ImageNet plus ImageNet, and the best one is an augmix, a method that uses diverse augmentations from auto-augment during training. And all of these models have improved robustness compared to a vanilla trained model. And as we can see, augmix has the overall best results because it improves the accuracy on ImageNet-C from 39 to 48%. With Gaussian noise, where we have trained with sigma equals 0.5, we actually outperform most baseline models on ImageNet-C without noises, apart from augmix. And we think that this result makes data augmentation with Gaussian noise a very powerful baseline since it's so simple and yet so effective. So the first key message is that data augmentation with Gaussian noise is a simple and strong baseline to increase robustness towards image corruptions. As a next question, we ask ourselves, is there a better noise distribution? Because Gaussian noise was a simple first choice, but maybe a bimodal one would be better. And how can we learn this distribution? So we train a noise generator, which is a simple neural network that takes Gaussian noise as input and produces a modified distribution as its output. The neural network is very small and simple. It has 4 layers with radio activations and only 1 × 1 kernels. Therefore, its receptive field size is also 1 × 1, and it produces an independent output. With independent, we mean that for every pixel, every image pixel, the value that is added or subtracted is sampled independently. So now we sample our noise from this modified distribution. Okay, so here's the objective function for learning our adversarial noise. X is the clean image, and delta is a sample adversarial noise. Then, of course, we want to clip the image values to the valid interval between 0 and 1, and also restrict the norm. Then we pass the clipped image through the network and calculate the cross-entropy loss with respect to the correct labels. When training the noise generator, we keep the classifier weights theta fixed. And we average the loss over all noise distributions and all images in the data set. And phi are the parameters of the noise generator neural network. So we train the noise generator to minimize the cross entropy with respect to the correct label to make them less likely for the classifier. The goal here is to find the most severe uncorrelated noise for a classifier. Now we want to see how effective is our adversarial noise. How would we evaluate that? We could see how much noise we need for a misclassification. So we sample noise, for example, Gaussian, uniform, or adversarial noise for an image. We then scale the magnitude of the sampled noise perturbation until the image is misclassified. And we refer to the minimal magnitude of this scaled noise of delta min. We calculate this delta min for all images in the test set and take the median. And now a small value indicates a more powerful noise because we need less of it to get a misclassification. And as can be seen in the results table, our adversarial noise is significantly more severe compared to Gaussian or uniform noise. Okay. And Gaussian data augmentation significantly increases model robustness towards Gaussian or uniform noise and somewhat increases robustness towards adversarial noise. We can now train the noise generator and the classifier jointly. The objective function looks similar to the objective function for training the noise generator, but now we also want to train the classifier. The intuition here is that once the classifier becomes robust to a certain adversarial noise, a new adversarial noise pattern exists that the classifier is vulnerable against. And by training the classifier and noise generator, for many iterations, the classifier becomes more and more robust against new adversarial noise patterns. We alternate between an outer loop of classifier update steps and an inner loop of generator update steps. To prevent the classifier from being stuck in local minima, we halt the training at regular intervals and train a new noise generator from scratch. We use a version of experience replay, which is a technique from reinforcement learning. We do not want the classifier to forget the adversarial noise patterns. It has already learned to be robust too, and therefore, for every classifier update, we also sample noise from previous noise distributions. Okay. During adversarial noise training, we learn different adversarial noise patterns and provide some visualizations here. We show actual learned distributions during adversarial noise training on the left in A, and how adversarial noise looks like in images in B. So far, we look at very simple noise patterns. Obviously, if our goal is becoming robust to a wide range of random corruptions, which typically have larger correlation lengths than 1 × 1 pixels, we should also learn more complex noise patterns. Okay, and as a reminder, this is the architecture that we use for our noise generator. To allow for more complex noise patterns, we have also trained a noise generator with 1 3x3 convolution, and the rest are 1 × 1 convolutions. Here we show example patches of 32 × 32 pixels, and also example images with this noise. We have tried further increasing the correlation length of the noise generator to 5 × 5 pixels, but did not see any benefits over 3 × 3. We have seen that Gaussian noise training leads to higher robustness towards common corruptions. Does this also hold for adversarial noise training? You have seen the baseline results and the models trained with Gaussian noise before. So finally, here are our full results with adversarial noise training. We denote the amount of correlations of the adversarial noise with either 1 × 1 or 3 × 3, depending on the maximum kernel size of the noise generator. SYN stands for sterilization, and we combine sterilization with adversarial noise training. We see that the robustness is further increased, and we get the best overall results for AMT 3 × 3 plus SYN in the last row. EP stands for experience replay, and here we see that we actually need it since the results get worse if we do not use it. So our second key message is that learning the distribution to sample noise from further increases robustness. Here is a list of the references I used for this talk, and please read our paper for more details. Thank you. Okay, that was my talk.
Yeah, thanks, Evgenia. So like one doubt I was having was like your objective more like seems like a standard like adversarial training thing like min-max objective. So I mean you are using a generator to generate an adversarial noise. So like why was there a need of a generator when I mean you can use some of the existing adversaries like PGD and all. I mean.
Okay, so the difference to PGD is that our noise is independent. So basically in PGD, you calculate a pattern for the whole image, right? And we basically only learn a distribution. So, our work goes more in the direction of universal adversarials, maybe, because with universal adversarials, you calculate an adversarial for all the images in your data set.
I see.
And we go even further than that. So we calculate a distribution for all images in a data set, and plus we also sample values for all pixels independently. So this is a very strong constraint for adversarial noise, basically.
I see. Yeah, so like if anyone has a question, please feel free to ask. You can also write them in a chat. Yeah, so I guess Surgan pointed out a paper ADV GAN and says like it generates adversarial samples somewhat similar to your one. So, I mean, do you have any idea? I mean, how? I mean, it's a GAN-based generation of adversarial examples.
Yeah, but it's not really adversarial examples. Because, as I said, with adversarial examples, like you cannot, if you have an adversarial example, you have this pattern, you can't really scramble all the pixels in this adversarial example that you have. And with our model, you could do that because our noise is independent.
I see.
Hello, Evgenia, can you hear me?
Hi. Yes.
Hi. Yeah. Hi, I'm Naveen. I'm a PhD student at Hyderabad. So you mentioned about experience replay from RL, right? So can you show some light on how exactly are you using that in order to store your previous? I didn't get completely of how you are trying to use that experience today. Can you talk about that?
Yes. So basically, with this GAN objective, we train the classifier against new adversarial noise patterns all the time. But what we also don't want, we do not want it to forget what it has already has learned to be robust to, and because this is something that can happen with GANs, and therefore so for basically when we train our classifier in every mini batch, we have the noise sample from the current noise generator, but also a part of the mini batch is sampled from previous noise generators. So we hope that this way, when we learn a new noise generator, then that it's kind of orthogonal to the previous ones, due to our adversarial objective. Sorry.
Okay. So So new noise generator, you mean a new distribution with different sigma, isn't it?
Well, it's not just Gaussian noise with a different sigma, right? I mean, we have very different distributions here. I mean, we also have bimodal distributions, for example, and so we kind of learned the space of distributions that can be modeled with our very simple neural network, and
Yeah. I was trying to understand what is basic intent of trying to learn. Trying to store and trying to remember the previous noises in the next iteration.
Well, basically what we saw, because we didn't have it in the beginning, what we basically saw is that so especially for 3x3 noise, we saw that once we did this adversarial noise training, that the accuracy went up and then it actually started going down again. And it didn't go up as much as it should, what we thought that it should do, basically. And then we started using the noise from previous runs as well, and then basically the performance just kept going up. So it is an empirical finding, but it is grounded in the fact that with GANs you want to basically prevent forgetting, right? So.
Okay. Thank you.
Yeah. So Evgenia, I have a doubt. So your immediate baseline, is it OGMIX?
I think so. Yeah, it is. It is OGMIX.
Yeah, so as far as I remember, so OGMIX, it randomly takes, a chain of perturbations out of given set of perturbations. So a natural question that comes to me: how about we train a reinforcement learning agent for that perturbation, choosing an optimal chain of perturbation? So.
Yeah, I think this work has actually been done in our lab, but I was not involved in that project. But yeah, sure. I mean, this is something that one could do in principle, but it's a different project, of course. But I mean, yeah. So I'm not sure how OGMIX does this. I think they actually just do random sampling. So they have exactly. But for example, auto augment. Auto augment is trained with the objective to maximize performance, right? For example, but one could think about redoing auto augment with the objective of optimizing some corruption robustness or something like this.
Exactly.
Yeah, sure. Yeah, but I don't work on reinforcement learning, but this is, yeah, of course, this is a valid idea what one could do.
Okay, sure. Thank you.
Yeah, so we have a question in the chat by Piyushi. So she
Yeah.
says like, could you please share some details on transferability of attacks generated by your method?
Okay, I mean, okay, so the short answer is we haven't tested this. But also when we wrote the paper, it's about transferability of attacks. Okay, so basically that means that we have our noise generator and we have our worst noise distribution, and the question is, would that transfer to other data sets? I think no. I think that it would not transfer. I think that the attack that we generate is basically always contingent on the data set. For example, what we have seen, because we also experimented with MNIST, we saw that with MNIST, for example, the noise generator learned to make all pixels kind of black, and because so what happens if you learn to shift the distribution towards negative values is that basically that all values in MNIST are mostly black, and then they don't add to the noise to the L2 distance of the noise at all. But you can basically perturb the few white pixels slightly, and this way have a very efficient noise distribution, so to speak. But basically this is something that would only work for MNIST because most of the images lack basically.
I see. Thank you.
Yeah.
Yeah. So one more like comment I was like having. So like you showed results on using synthesized like stylized ImageNet plus your method ANT method. So I was just wondering like we have a generator which might be able to generate a stylized version of the images in that particular way. I mean, maybe use some kind of StyleGAN or something to maybe find some kind of, you can say, adversarial or some kind of stylized transformations that can help, because in general I see that stylized transformations does lead to a very decent gain in the robustness to common corruptions. So I was just wondering, I mean, if you can share some lights on that. I mean, if you have any idea.
I'm sorry, what is the question again? Why that is, or what's the question?
Yeah, so the question was like this. So I was just wondering how can like we have a generator that can maybe produce some adversarial stylized versions of a particular image, and then we can just feed those kind of images to generator.
Yeah, one could do that, I suppose. I mean, we have okay, so basically this idea of learning distributions, I think was novel enough that we could just do the most basic thing and and get people interested by it. But so basically the noise generator is super simple, right? It's just 4 layers fully connected. It would not be able to produce something that elaborate as stylization or something. And also we basically produce additive noise. And in principle, one could think about defining an objective similar to what has to be done to create stylizations, but then one would have to work with an image-to-image network and not with a network that only produces additive noise, basically. But this is a possible extension, I suppose, that one could think about.
Mhm.
Yeah.
You see.
Okay.
Yeah, so Evgenia, one last thing. So did you test this on unseen noise? I mean, noise that wasn't a part of training somehow?
Yes, we do. I mean, that's why we report ImageNet-C with noises and without noises, right? I mean, we do that with Gaussian. If we train with Gaussian noise, we'll probably maybe overfit to the noise corruptions of ImageNet-C, but we also test on images without noises. And there we also see that we get better.
I see. Yes.
I see. Was there any trade-off?
Yeah.
Yeah. So was there any trade-off in the clean and the robust, accuracy?
Yeah, sure. I mean, of course. I mean, we do, as with any regularization method, I guess, we do lose clean accuracy and get higher robust accuracy. But I mean, that's pretty much expected.
Yeah, I like methods like Augmix and all, they do achieve a pretty much decent clean accuracy also. So
Yeah.
as compared to like standard adversarial training techniques, they usually have a large trade-off large gap in.
Yeah,
So,
sure. I mean, we lose like 1 or 2% on the clean image, so that's like others do as well.
Yeah.
So yeah, maybe in the next steps, maybe do you somehow see yourself training on the corruption such as warping and perspective changes? I mean, I'm not sure if there will be such linear learning such as this. Maybe some more parameters may be required.
Yeah, I mean, we're thinking about doing more to try to model more broader noise distributions, because I mean, as ANT is currently very limited. It's only distributions or so yeah, of course we are thinking in those terms, but it's not very clear right now what the next steps are going to be.
Okay. Yeah. Thanks.
Yeah.
Okay, so yeah, maybe we just wait for 1 minute to see if there are any more questions, and then we can move on to Stefan's presentation.
Sorry, I left. Oh.
Yeah, so I was just saying maybe we will wait for a minute or so to see if there are any more questions, and then we can move on to Stefan's presentation.
Sounds good.
Yeah, okay. So like we will move on to the next presentation by Stephen. So he will be presenting the paper Improving Robustness Against Common Corruptions by Covariate Shift Adaptation. It was accepted recently at Neuralnets. So over to you, Stephen. Yeah, you can start.
Yeah, thanks a lot. In general, thanks to Puneet and everybody involved in organizing this ResearchConnect series. And yeah, welcome to this talk on improving robustness against common corruptions by covariate shift adaptation. Evgenia was also involved in this, so here we have the advantage that you can ask questions to both of us later on. And then our other collaborators are Luisa Eck from TU Munich, and then Oliver Brinkmann, Wieland Brendel, and Matthias Bethke from the University of Tübingen. And very similar to before, the general idea behind this work is that ImageNet models are typically evaluated on this IRD setting, but in many practical applications, we're actually interested in the robustness of a particular algorithm and its behavior when we test it on non-IRD settings. So for example, in autonomous driving, we could have different weather conditions. In photography, we could have different noises induced by the camera sensor or by shaking your camera. And on all these corruptions, we kind of still want to maintain a good performance without necessarily knowing them beforehand. And to this end, ImageNet-C is a nice benchmark comprised of different artificially induced corruptions, which makes it kind of content-wise the same as the validation set of ImageNet. But then we kind of have this possibility to add different holdout corruptions, which you can use also for parameter tuning, and a few test corruptions, which are kind of previously unknown corruptions that we want to become robust to. And the metric that we're typically considering, since this is kind of a lot of different scores that you need to summarize in the end, is the mean corruption error, which is in a sense the relative improvement over an AlexNet baseline model. And this is essentially averaged across all these corruptions. And in this metric, we want to get as low as possible. Yeah, and then maybe thinking a bit about the motivation here. So the first issue that we have in the current robustness evaluation setting is that most work focuses purely on an ad hoc setting. That means you are given access to one sample, and then from sample to sample, the corruption that you're testing on can completely change. And you basically have no information whatsoever about which condition you're actually now testing on. And then in many practical application settings, that's definitely interesting, but we can think of many settings where this assumption is actually a bit too strong. And these settings could be things like medical imaging or quality control. And there we could assume that we have at least access to a few samples where we know that they are roughly taken under similar imaging conditions. Or we could even have some batch processing system where we are given a lot of images, maybe thousands or even more. And then we can certainly do better than making this assumption of this ad hoc evaluation setting. So the conclusion here is basically in some settings, you're actually able to adapt to the test distribution a bit. And then the second issue is that many computer vision models are trained with batch normalization. There are alternatives out there, which I will come to in a bit. But this is kind of still the predominant setting during training. And then if you take such a model, you typically just transfer the statistics of this model to test time. And in a bit, I will kind of outline a potential issue with this. So overall in this work, the kind of underlying hypothesis is that the current robustness results that are reported underestimate the model performance when you actually can have access to more than a single sample from the test distribution. And the goal of this work is to outline the gains a bit when you apply a simple baseline model on ImageNet-C and also some other data sets to actually improve in this adaptation setting. So just briefly revisiting how ImageNet-C robustness is typically benchmarked. So you take a model, you train it on ImageNet, and then you take that model and weight by weight apply it on each ImageNet-C corruption, and then you record the score. And as I told you before, you can then kind of do this for every corruption and get a mean corruption error. And then the fundamental problem here is, or potential problem at least, during training, you use these batch normalization layers, which on the fly compute their statistics. So each layer coming after a batch norm layer has the implicit assumption that the statistics in the previous layer were normalized, because that's essentially what the batch norm layer is doing. And in an IRD setting, this assumption is also fulfilled at test time. The issue is now if you have a shifted distribution. So here these orange distributions, which are slightly smaller and a bit shifted, then this assumption is violated after essentially every batch normalization layer. And then maybe the model is robust to this, but in general, what we can note here is that the assumption that you can simply transfer the statistics is potentially not optimal in this covariate shift setting. So the fix here is to simply re-estimate the statistics on the test set. For that, you need a few samples from the test set. And in this first new evaluation setting, we basically assume that we have access to the full test data set. So think of you're given all 50,000 test images at once, and you can then evaluate on them. Of course, you don't have labels, but you can certainly recompute the statistics. And then there are some settings which are a bit of an edge case, so where you have more than one sample, but also not too many samples, maybe something like 8 samples. And here it's a bit difficult to accurately estimate the statistics on the test domain. And what we propose here is to do something in between. So you leverage a few pseudo samples from the training set, and then weight the statistics of the training and the test set, and then you can still get a faithful estimate of the statistics. Yeah, and kind of still leverage that you kind of slightly nudge the model towards the correct distribution. So looking at some results, how this works out in practice. So in this plot, you see a few baseline lines. So the black line is the currently best model, or the best ResNet 50 based model, deep augment and augmix. And then we here consider two other variants of ResNet 50. So the one is this vanilla ResNet 50 model, and the other one is the augmix model. And what we see is, if we now take a few samples from the test set and recompute the statistics for this normal ResNet 50 model, then as soon as we have more than 8 samples available, we basically surpass the baseline model performance. And in the limit where we have many samples, we get a gain of roughly 10 to 14 percentage points for this model. And then the other variant I just talked about, so we see kind of from less than 8 samples, we can't correctly estimate the statistics. This is mainly a property, or I mean, it's mainly due to the fact that if you only have 2 samples, you can't faithfully estimate this mean and variance of the activations. So here we now leverage this prior. So we have a prior on the target on the train domain, and then we leverage that prior and only slightly correct it, and then we can see that also in this range we improve a bit. Just briefly looking at how this works out for an augmix model, which is a bit more robust. So we now here have a small gap between the models, which is attributed to the fact that the augmix model is a bit more robust. And also in this case, we kind of can transfer this additional improvement and also apply both our technique in the full adaptation case and in the partial adaptation case. So the message here is a bit that robustifying a model is more or less orthogonal to this adaptation technique. So next, we considered a broad range of different robust models. Also, in the past month, there was a bit of progress here, also appearing at NeurIPS. So especially these families of deep augment models came out quite recently. And what we see here is the baseline performance of various models. And we see that, so this is roughly chronologically ordered, and kind of over time, the benchmark was improved quite a bit. These are all ResNet 50 architectures. Only the last model is a ResNext 101. So that's something to keep in mind. So because here the model is simply larger. So now we consider our partial adaptation case, and we see that we already get a huge boost. And again, this is for a 1,000 class problem with only 8 samples available. So probably it's reasonable that in many practical settings, we actually have these 8 samples. And then if we look at the full adaptation setting, we improve even more. And if you actually admit that you can evaluate under the setting, then you would actually get a new state of the art for a ResNet model of 45%. And for this larger deep augment model, you end up at 38%. A mean corruption error. Okay, so this is the first experiment looking at how that technique transfers to robust models. And the takeaway, as I said, is that robustifying a model is more or less orthogonal to this adaptation. So we next ask, is it also orthogonal to the model architecture that we use? And for that, we use all models available in the Torch Vision library, along with their publicly available checkpoints, and reevaluate them. And here you see these white filled circles, which are the baseline performances of different models. The color denotes the model families. And you see that the MCE is essentially improved for all of these models after adaptation. And also thinking a bit about the question that was raised earlier, here you can also see the trade-off in terms of how much do you lose on ImageNet when you apply this adaptation, and you see that there are some slight variations which also depend on the model family, but overall, especially for the well-performing model, the drop in ImageNet performance is not very large. So next, we want to understand a bit better what kind of information is captured in these statistics. So the experiment that we do here is we take the optimal statistics that we obtain on the training set, which is ImageNet, and the optimal statistics that we obtain on each of the corruptions, which you can see again summarized in this table over here. And then the different categories are colored in the same way. And what we see here is that essentially if you compute the Wasserstein distance between the train statistics and the test statistics and average that across layers, then you get a metric which correlates quite well with the performance drop that you get when you evaluate the vanilla model trained on ImageNet only on each corruption. So kind of the distance between the optimal corruptions and the actual the optimal statistics and the actual statistics you're using is quite informative of the expected error that you get on the test domain. And interestingly, this also holds true after you apply our adaptation technique. So even after you correct all the scores, this linear relationship still more or less holds. And a potential application of this is that kind of unsupervised, you can also already roughly judge what kind of performance degradation you can expect on an unseen domain just by calculating the statistics. Just very briefly, here's the reverse case. So what happens if you kind of take an ImageNet model and evaluate with the wrong statistics obtained on each corruption? And here here the relationship is a bit more complicated, I would say, and it also maxes out at 100%. But I think the bottom line is still that the Wasserstein distance is indicative of this increase in the test error. Some more ablations and limitations of our method. So I previously said that it's quite robust to the model architecture and also to additional means for robustifying. What we found is that if you take models which are trained on much more data and potentially also with semi-supervised schemes, then at some points the gains diminish. So the experiment here is to take a ResNext 101 model. The first row is trained on ImageNet. So here you get the same gain that we reported before. The next row is trained with a modified scheme using semi-supervised training on a 3.5 billion images dataset from Instagram, which is recent work out of FAIR. And here we basically see that with exact the same model architecture, the gain essentially vanishes. And if we look at an even larger model, then we even see that that the method slightly makes the results slightly worse. So the indication here is that the statistics that you obtain by training on this very huge data set are already reasonably good to work on ImageNet. The other ablation study that we performed is looking at other normalization layers like group norm and initialization techniques like fix-up, which don't require any normalization at all. Because the primary reason for training with batch norm in the first place is typically an optimization reason. And what we see here is that for the ResNet 50 family, when we take a non-adapted batch normalization model, this is generally worse than either using fix-up or group norm. But once we start adaptation, we kind of outperform both the fix-up and the group norm model. And the takeaway here is kind of the best ad hoc technique might not be a batch norm model, which you don't adapt, but instead just using techniques which kind of work without applying batch normalization. But if you have enough samples to adapt on, then adapting the batch norm layers is definitely a good choice. Some other exploration of limitations of the method. So ObjectNet is also a dataset with distribution shift. But this distribution shift, as you can see, is much more involved than the one that you have in ImageNet-C. So in ImageNet-C, you have you take an image and then you corrupt it in a certain way. On ObjectNet, you kind of have the situation that you are taking new photographs, for example, of objects like this chair in the top row from unusual positions. So it's much less systematic and it's much less clear how to kind of adapt here. And applying our technique shows that you get a very slight gain, but overall, compared to the huge gap that you have compared to the ImageNet performance of this model, I think this is not really worth mentioning. So on this data set, there's certainly a lot of follow-up work to do, also involving more involved adaptation schemes. So we next ask, is this purely because the images in ObjectNet are actually natural images and that makes the whole task hard and impossible to do? Or is it rather because the distribution is more mixed up and we don't have really this situation of having systematic distribution shifts? And for that, kind of in the meantime, this new data set, ImageNet R, was introduced. The R stands for renditions. And here we have a couple of ImageNet classes, and then a collection of images where images are hand-drawn or depicted in some other forms, but that are essentially not photograph images. And what we see here is, while the gain is certainly smaller than the one that we observed on ImageNet C, again, the colored lines the colored lines depict the adapted performance, the black lines depict the baseline performance. So what we see here, that the gain that you get with adaptation is roughly on the same order of magnitude than the gain that you get with successive techniques for robustifying the methods. So a baseline adapted model is roughly as good as a non-adapted outmix model. And overall, taking the best model, again, deep augment here, along with adaptation, further improves the results. So again, we have a look if this is kind of model dependent, and again test our full family of robustified models. And again, what we see is that after adaptation, we get like a consistent improvement, maybe except for this model where we only get like 2% points, but overall we get like a consistent improvement of 4 to 5% points, also in ImageNet, R. And then kind of the final ablation here to stress this point that I made before. So if we look at this ablation study again, where we take both group norm and fix up, which are techniques where we don't use batch normalization, and then we consider our adapted and non-adapted batch norm model variants, then what we see is that on ObjectNet and on ImageNet C, where and on a mixed version of ImageNet C, where you basically shuffle all the corruptions, on these data sets where there's no systematic shift, the group norm and fix-up variants are essentially performing best. But as soon as you switch to systematic corruptions, then this adaptation scheme where you re-estimate the parameters for each systematic corruption or data set shift actually improves, and you outperform both the non-adapted batch norm, the group norm, and the fix-up models. So I think this is the main takeaway. If you can adapt, then using a batch norm layer is actually beneficial. Okay, so to conclude, in our main result, we empirically showed that batch norm adaptation, which is also a well-known technique previously explored in domain adaptation in general, improves all commonly used models on ImageNet C, which in particular means all architectures in torch vision and also all kind of robust defined techniques that we were aware of when doing this work. And often this gap is actually quite large, so 10 to 15% points can be leveraged by that. And kind of the conclusion that follows is that if you only focus on the ad hoc scenario, there might be some interesting evaluation settings that you miss. And with this paper, we propose to broaden the robustness evaluation protocol a bit and also consider a partial adaptation scenario. A sample size that we find reasonable on ImageNet would be something like 8 samples. And the full adaptation scores when you can basically adapt to the full test distribution. And yeah, when evaluating kind of in these two settings, then batch norm adaptation is certainly a very strong baseline, which is very simple to implement. But we expect that in future work, there will be more involved techniques, possibly transferring more involved methods from the domain adaptation that make sense in these evaluation settings. And then if you're interested in reading more, or also looking at the slides afterwards, please head to domainadaptation.org/batchnorm and have a look at our paper. And with that, I want to conclude and thank all the people involved in the work. Most importantly, also numerous people in the Bethke and Matis labs who were involved in getting good suggestions. Also the anonymous reviewers at Neuralnets, who proposed basically all these nice ablation studies about ImageNet R. Yeah, and finally my two PhD advisors, Matthias Bethke and Mackenzie Matis. And I think now there's some time left for questions.
Yeah, thanks, Steven. This was really an insightful talk. So yeah, I have a question. So like I was just wondering how this particular batch statistics adaptation is scalable in like real world things. So I mean, in the experiments you have showed that you have an ImageNet, you trained a model on ImageNet clean, and then you are taking samples from a corrupted benchmark. But let's say like in real world things, we eventually want a model to be, I mean, robust to even corruptions and renditions, ImageNet or also. So let's say we have some samples of corruptions also, and let's say we have some samples from ImageNet R dataset also. I mean, let's say we have a line of these kind of different corruptions and distributions. So, I mean, how reliable is this particular thing in that particular case? I mean, currently, I mean, you have shown on like a single distribution shift, but like if we have samples from multiple distribution shifts, how can, I mean, we can adapt?
Yeah, that's certainly a quite good question also regarding the practical applicability of this. So I think there are kind of two answers. So the first one is one very crucial property that the samples that you want to adapt on should have is that they are sampled across different classes. Because one thing that you certainly need to do is to marginalize at least a bit across different classes. And if you would only, let's say you have only squirrel images in your adaptation pictures, then most likely the technique will fail. And in fact, so one test that you can do is if you apply this on an unshuffled data set for adaptation, then the technique essentially doesn't work because you can't marginalize it. So that's kind of the first thing to keep in mind. You need samples from different classes. The second part of your question was more addressed to the fact or to the setting where we have different corruptions and we're not completely sure which ones we evaluate on. Is that correct?
Yes. I mean, eventually we want a model to be robust to, I mean, different distribution shifts. But let's say we already have some samples, but so, I mean, is this really scalable in that particular setting or?
Yeah, so I think in the way that we propose in the paper, it's first of all solely applicable in this batch evaluation setting where you are essentially sure that all images that you have some short systematic shift, which, for example, could be true in medical imaging where you have different scanners or microscopes, and you know that essentially all images come from a single microscope. And then you also roughly know, okay, the errors and the noise, or also the color appearance and other things of this scanner will be similar. So I think in this setting, it's directly applicable. In the setting that you outline, where you basically don't know which image you kind of need to assign to each corruption, I think there's some additional engineering necessary. I mean, one strategy here might be that you train some sort of oracle model that first groups your corruptions in some sense. But yeah, that's I would say it's certainly a solvable problem, but it depends a bit on the application that you want to tackle in the end. Essentially, how easy it is to distinguish different corruptions versus how hard it is to actually solve the classification problem in the end. I think if you have a setting like here where it's relatively easy to kind of distinguish the different corruption types, that would be my intuition at least, but it's hard to infer the class. There, this technique is definitely applicable. But if the distribution shifts are a bit more subtle, like the ObjectNet case that I outlined, where you have where the distribution shift can be that the chairs lie on the floor, for example. So that one is much harder to detect. So I think it depends a bit on these aspects. But yeah, I mean, I think the takeaway also from the ablation in the end with like the mixed ImageNet-C is you need some mechanism for sorting your input images into different groups which have a similar systematic shift.
I see.
Did I answer your question?
Yeah. I mean, I was more like concerned, like how can we scale it really to a continual learning type of fashion? I mean,
Oh, I see.
let's say we have some particular kind of corruption right now, and in future we like observe some kind of corruption, then we want a model to be robust to all the seen corruption so far.
Yeah.
So I mean, we keep on like adapting these batch statistics as we move on. So I mean, is it really?
Yeah.
I mean,
So I mean, let's maybe consider the setting where you're given a stream of images. I think this is roughly what you're thinking of currently. So if like a continual adaptation setting where you have a stream of images, and then the assumption here is that kind of the frequency of changes in the corruption doesn't change between each image. But instead you kind of have, let's say 1,000 images are roughly from the same corruption, and then you have some transition, and you basically go over to the next corruption. And one very easy trick that you can apply here is to simply keep an exponential moving average of the matching statistics, which is actually, so in these controlled evaluation scenarios, we didn't do it, but we played around with this a bit. And kind of the most efficient way to also do this full data set adaptation is to simply do a running, doing kind of a moving average over all samples that you have seen so far. And then to cover the application scenario that you set, the parameter that you essentially need to tune is how fast you want to discard the past experience and how much weight do you want to assign to the newly samples. So I think that would be the closest.
yeah, I see.
So I have a side or a follow-up question to this. So can we take something like this as a takeaway from this? So basically here for adversarial robustness, so for robustness, basically the covariate shift or the domain adaptation kind of thing is helping. So does that mean, so let's say I'm training a model on MNIST. So during the training around at a particular interval, I also try to adapt the model to another data set, which is kind of an SVHN kind of data set. So does that mean adapting to more data sets during the training itself rather than doing it post training will give robustness? Like, can we take something like that as a takeaway from this work?
I mean, there certainly works exploring these trade-offs, but I think in our work we solely focus on the scenario that you have a trained model and without computing any gradient, you adapt it to the test distribution, right? So also in our case, when you so you don't really gain performance on ImageNet by this technique, right? Because what you essentially do is for each severity, you kind of choose the optimal parameter setting for normalization. And what you're highlighting goes more in the direction of doing something at training time, if I understand it correctly.
Yes. So while doing adaptation during the training time itself rather than post training, like any thoughts on that? Does that
in
robustness directly?
I think in I don't know, maybe Evgenia can also comment on this later on. But I think, I mean, in general, the setting that you have, so also if you think about models like AugMix, or also the stylized ImageNet training that I showed in the table with the robust models. Yeah, so if we think about these models, I mean, in a sense, they are already trained to also work under these corruptions, right? So they are not trained to kind of adapt at training time to a new corruption. I think that's kind of the direction that you. So the question sounds a bit like some sort of meta learning approach, right? That
Yeah, something like that. Yeah.
Yeah.
I see the point. So everything which is kind of done in this setting, the current setting in which your work is positioned, is after you have a trained model.
Exactly.
Okay.
Yeah.
Yeah. Okay. I see.
So
Okay.
I think the idea that you outline certainly makes sense, that you kind of also during training learn a representation that has somewhat that is adaptable, for example, right? I think if you already know that you want to adapt during test time, then it's good that your representation, I mean, if you can't make it robust or invariant, then it's kind of important that you make it adaptable. And in that regard, kind of what we see here, that there are certain choices in the model architecture that you can do there, right? So if you take a batch norm trained model, then you can adapt it. If you use something like a group norm model or fixed up model, at least with this technique, you kind of can't do that. So yeah, and I think it might be actually interesting to think about also tweaking objective functions in a way that kind of allow. So what you typically want to have is, if you want to adapt at test time, you have some unsupervised objective for adaptation. And what you want to achieve is that essentially when you tune that objective during test time, you are actually going into the right gradient direction, so to say, right? So there are few works out there going in that direction, and typically what you do is you train this unsupervised objective along with the supervised objective during training time, and then at test time you switch off the supervised objective. But because the gradient signals of both the objectives point in a similar direction, you can gain some additional improvements during test time as well. I think something like this goes into the direction of answering your question, potentially.
Yeah, got it. Thank you, Stephen. Thank you.
Yeah.
Stephen, I have a question. Can you hear me?
Mm-hmm.
Yeah. So as far as I can see, so when we have a fixed batch norm, we have a batch norm parameters. So you try to adapt it to the corrupted sample so that we can have a broader space to project. So what I was thinking is still it's a batch norm with fixed set of parameters, right?
Mm-hmm.
So because now if you predict new distribution, you will lose something there, because at the end of the day their batch norm may be having some constraints about how well you can cover the entire space.
Yeah. Okay.
So that's what. So how do you see this key? Do you lose a lot of information by shifting it to the corrupt thing, or what is your take on this?
So maybe to clarify the question, is the question in the direction of if I So that kind of based on the model architecture, I can only do certain things with this adaptation technique. Is that the direction that you're heading, or do you have some?
Maybe yes. So it's more like when I predict new set of parameters. So it's essential key. Okay, the information that was stored in the previous set of parameters, it is sort of shifting also. So at the end of the day, it is still a batch norm, right? So you cannot have a batch norm which can enclose both of the informations. With a similar performance.
So you mean between the training and the test domain?
Yeah, exactly. Yes.
Yeah.
So inherently, it seems to me that there will be a loss all the time, because the parameters have to shift, and some of the information has to loosen up.
Yeah. So that's definitely the case. So you always need to have separate statistics for the target and the source domain. So basically, once you adapt the statistics, you will. So that was actually it would be this case. So you're basically so the points that you see plotted here is basically you take the statistics that you adapted on each of the corruptions, and then you test that on ImageNet. And what you see is that this actually quite severely affects the performance. In some cases, it drives up the error to 100%. So yeah, that's certainly a limitation. So you need to keep track. So you need a domain label essentially, right? So also for the clean domain, and for all the kind of test domains, you kind of need to keep track of a separate set of parameters. But so that being said, so very initially, maybe going back to this intuition. So I think the main problem, or the main reason why this technique works in the first place, is this assumption that you bake into your model when you train it with batch normalization at training time. So you basically train each layer so that so each layer essentially assumes that it will get normalized statistics from the previous layer, right? And that is essentially the assumption that's violated when you evaluate on ImageNet-C, and that's what the technique fixes. So that also means if you have a model, for example, this weakly supervised trained model, so here you would have the setting that the kind of the statistics that you have on ImageNet already transfer well to ImageNet-C. So there's not much to adapt. And then, of course, the technique doesn't really help anything. So I think it's kind of useful to have this in mind, that kind of the gain that you get comes from, or most likely comes from this notion that you kind of corrected this violated assumption of having normalized statistics in the network.
Okay, yes.
Yeah.
So a follow-up question will be, so I mean, you said normalized statistics usually are usually pre there in a lot of cases, but there has been maybe some questions regarding normalizing is restricting this distribution. So I mean, would you comment on relaxing this constraint or removing few layers in between so that the shift does not happen predominantly in all of them?
Wait, but so the model, I mean, you're not actually throwing away information, right? Because at training time, you did exactly the same thing. You also batch-wise computed statistics and normalized your activation maps. So you're not doing anything on top. It's more like so at evaluation time, you treat the model as if you were in training time. That's I think the main difference. So it's not that you kind of removing anything. The thing that you switch is, instead of using the statistics estimated on the training set, you recompute them. But in both cases, you would kind of center and normalize your activation maps.
Okay. Yes, I think that answers my question. Yes.
Yeah. Yeah. So in that regard, maybe going back to yeah. So basically, what happens inside the network after each layer, you normalize, or I mean, you kind of apply this transformation that you take the feature map, then subtract this mean, and then divide by your estimated standard deviation. And kind of the choice is, do I want to take the statistics from the train, the test, distribution, or something intermediate? And the question is, what performs best? And yeah, and I think the claim does not go much beyond that. So I think the takeaway is simply, if you take the statistics that make the activations zero-centered and uniform with uniform variance, then at least the computer vision models that we considered perform best. Yeah, but you don't. So I think the point I wanted to make, maybe to conclude, so you don't strip anything away, or you don't change anything in the model. It's just a different way of choosing these parameters for normalization.
Yeah, so one more thing. So like, do you have any idea on how can we do like this similar like batch adaptation in case of generative networks? I mean, let's say we are given, let's say 10, 15 examples of particular corruption, and we want to generate similar looking ones. So, I mean, how can we kind of adapt generative networks in that particular setting? I mean, one way I can think of is that what you do is you take the discriminator and you kind of adapt and from the newly adapted batch statistics, and then you just assume that this particular discriminator now works well for that particular corruption thing, and you just train the generator. So yeah, so I mean, do you have any other insights on how, I mean, this particular thing can be achieved in case of generative networks?
Yeah, I think as far as I know, there are a few works out there doing something in this direction. So I think what you want to have is, if you have, so I think you're talking about the case where you have kind of different different styles in which you can essentially render the image, right? So I mean, it could be a corruption, but it could also be a style applied to your style transfer, for example. Maybe that's actually an interesting example. So I think there are these networks who render an image with a particular content in a particular style, and they are actually using something very closely related to this. So there you kind of have have this domain label, which would in our case be the corruption label, but it could also be something else. And this domain label essentially changes something about the generative process in the network. And the works I'm aware of actually adapt the affine parameters along with the batch normalization statistics. So this goes in the direction of what you're saying. And then you basically have a bank of different parameters for this process. And kind of, and based on which style you want to apply, you kind of take out one bank and then you generate the image in that particular style. So that goes a bit in that direction. And I could imagine that in gun training, people also thought about these things, but there I don't have an intermediate pointer right now.
I see.
But I think in general, looking at these techniques for fast neural style transfer might be interesting in that regard. So I think the architectures there go really in that direction.
I see. I mean, I guess, I mean, the paper you were referring, like, was it batch statistics adaptation for small data set generation? I mean, I'm familiar with the paper which does something like batch adaptation. So like, but it's slightly different because in your work you were kind of you're changing the parameters that normalize a particular input in batch norm. But
Yeah.
in that particular paper, they were scaling. They were actually tuning the scaling and the shifting parameters that you do after normalizing. So I was more particularly interested in how we can do this particular thing, like, because this is particularly relevant for, let's say you have some covariate shift in a particular data set, then this particular thing is really helpful rather than just fine tuning the scaling and the shifting parameters.
Yeah, I mean, you're absolutely right. I mean, typically what you do is, in a sense, it's the inverse thing, right? So what we do is we kind of normalize the feature map and kind of correct it that is done properly on the test domain. But in a sense, in generative modeling, I'm not even sure if that's what you want to do. I think in generative modeling, it's more that you want to do the inverse case, right? So based on a particular, so you kind of start with a common representation, and then based on the condition that you want to generate, you need to kind of shift the distribution in place A or place B. I mean, I think it might still make sense, even if you have something like this, to compute the normalization statistics separately for each for kind of each condition. Yeah, but I think, or at least my intuition would be that it's a bit hard to transfer insights directly to generative modeling. I think it was quite the opposite, actually. So this technique as such, or I mean, many variants of this, I think, were proposed over the past years. And I think this work was more about actually pointing out, if you take this baseline, which is kind of established and well known, it actually works surprisingly well for robustness evaluation and this evaluation on renditions and on kind of full scale ImageNet data as well. I think it was a bit the reverse way. So it's not that you can potentially transfer this to another thing, but it's more like there's a large family of different adaptation and modulation techniques out there, and we picked one particular one that's suited for our evaluation case. I think I would phrase it that way around.
Yeah, I see. I mean, I think there are two different kind of things. I mean, one way is how you can project the corrupted sample to the same distribution that I guess you are particularly doing. And one other thing is how you can generate a particularly different kind of distribution that I think which deals with tuning the batch shift and scale parameters.
Yeah.
I think, yeah.
Yeah,
I see.
because you want to add information, right? You don't want to remove
Yeah.
it. You want to, yeah. I agree.